This is going to be a presentation, as Maria said, with two parts, question and answers in the middle, and we'll have a little break there in the middle. The first half is going to be primarily the background, and the second half will have an example that we can look at. So if we think about rigid walls or rigid vertical elements resisting lateral forces in seismic structures and one-story buildings with flexible diaphragms, this is pretty much what we're looking at in this picture, as you see here. When we think about logistics or transportations of goods, warehousing, this is quite common in these types of buildings, these low-rise big box buildings. In addition, these types of buildings are usually rectangular, but not always, and we'll talk a little bit about the problems associated with trying to analyze these when they're non-rectangular and really outside the method that I'm going to be presenting today. This is a timely method in that the Wall Street Journal yesterday had actually an article about the problems of getting materials from China through our ports and into these warehouses. And the warehouses that are typically near these ports are at full capacity, and there's very little vacancy, and so there is a shortage of warehousing at this point, as well as the logistics of trying to get them from the ports to the warehouse. So it is a problem that we're experiencing today. My outline, I'm going to be going into an introduction about this type of procedure, diving then into the numerical modeling research that was done, and looking at both a wood structural panel diaphragm and some discussion about bare steel deck diaphragms that were done. And then some additional site studies were looked at regarding wall anchorage of these buildings, building heights, looking into the effect of that, and some P-delta stability studies that were undertaken. So the numerical modeling, I'm going to talk about that briefly here to begin with, about how we analyzed these buildings in preparation of this new methodology. First of all, let's think about a rigid wall flexible diaphragm building as it was originally known, but it applies not just to rigid walls, but if you have rigid brace frames, it can apply just as well to that. And these are typically going to be concrete or masonry wall buildings that are relatively rigid and plain, but not always. As I mentioned, it can have brace frames and a big, large diaphragm. Often here on the West Coast in high seismic zones, the predominant diaphragm of choice in these buildings is a wood structural panel diaphragm. More common now, they're actually attached to steel open web joists with a wood nailer, but the diaphragm action is still based on the wood structural panel. And it's relatively flexible and plain. The big box retailers, Costco, Target, Home Depot, of course have this type of building system very commonly, but they're also found in the distribution centers for warehousing, logistics. So these buildings are quite common in a urban area. Under construction, this picture here that you can see a concrete tilt-up building. Those little doors you see are actually full 8 by 10 foot truck doors. This building is over 1 million square feet in California, and it's just a very, very unique building style that gets replicated quite a bit for warehousing and big box retailers. The behavior of these buildings is quite unique compared to most of the buildings that we would otherwise be engineering. The diaphragm has very large deformations, resulting in a long period of vibration. Where the shear walls are short and stiff, they're going to have very small deformations, resulting in a very short period. So this diaphragm dominant design plays quite a bit into how they perform in an earthquake. So the seismic response is primarily dominated by that flexible diaphragm with the long period. But current practice in buildings assumes that the frequency of the building and the behavior of the building in a seismic event is really dominated by the vertical elements. For example, the period of a building that currently in ASCE 7 is approximated with a factor C sub t based on whether it's shear walls or moment frame, and then the height of the building, H sub n, the height to the roof. So the period is believed in this equation to be approximated based on how tall the building is in a conventional structure. And this is really inappropriate for this type of building because we find that the behavior of most of the mass in the building is oscillating at a period more associated with the diaphragm, not the height of the building. In addition, if we're looking at the seismic strength of these buildings, current practice assumes that the vertical elements are the ones that go inelastic. So we have a response modification factor, R, which is associated somewhat to the ductility of the vertical system, and then the overstrength factor, omega, which is also based on the ability of the vertical system to withstand excessive loads. It's all based on the vertical system, or in a rigid wall, flexible diaphragm building, it's based on the walls.